estudo de computação. Então, quando o cara da engenharia quer colocar uma matéria, aí o de computação tem que pôr um também para não ficar desigual. Aí os caras vão colocando, daí agora eles estão tentando tirar. Eles perceberam que isso aí não é uma boa ideia.
Não sei se ele botou Today is our last day here, and we will cover at first the problems of the previous contest, and after it will be a lecture. So let's start. Sub-regional contest of my university was offered you as a previous contest. I was a chief judge on this contest, and I hope you liked it. Okay, problem A. Problem A was a kind of implementation problem. There was a kind of grid, and you were moving between cells, and the current state was defined by three values: current x position, y position, coordinate, and the direction. And the problem was to simulate the movement and to calculate some function, but all you need is just to understand how movement should to be processed and what are the neighboring cells. Then you go along a block, a monoblock. Okay, so it was just implementation problem, and it was enough to store three variables, x, y, and direction. And about problems like this, it is always good to avoid large number of ifs in your program. For example, here it was a good idea to have an array of directions, say dx and dy. For example, left turn, it will be just +1 to direction modulo 4, and right turn becomes +3 modulo 4 in terms of direction. Also, if you go through the space between blocks, you need to find these two blocks, and it is easy to find them just using also these array of directions, because you can just look on the left and on the right and locate coordinates of left block and right block. And to implement this solution, just Boolean square matrix for each block is enough. I think that it was one of the easiest problems here, and most teams have solved it. The next problem is Kakura, and it wasn't an easy. The problem was about the puzzle, and you were given the description of puzzle, and your task was to find a solution, any solution for the puzzle. The puzzle looked like rectangular grid, and some cells were empty, but some cells contained information in them. for example, 10, 17. Each non-empty cell was divided on two parts, as it is on the blackboard, and the number here is the total, the sum of all numbers you should put in empty cells here. So the sum of numbers you should put here should be 10, and you can only put digits between 1 and 9, and in each such space they are called runs in the statement. All digits should be different. So, for example, here I don't know how to remove it. Okay. Here there is a puzzle and its solution, and your goal was to find any solution. This puzzle can be solved using brute force algorithm, but you need to implement some heuristics, some optimizations to fit in strict time constraints. And let's look into solution and discuss it. This solution uses some pre-calculated arrays. You see there is an array bit, just power of 2. You see here bit count. It is just number of bits in the given mask. You see here array sum. It stores the total sum of given subset of digits, and subset of digits is represented by mask, by binary mask, and one more, a bit of tricky array. It is array D. If we speak about the state of run, it described by the following variables. It is the length of run, and we need to reduce it. If we put some digit in empty cell, we should reduce it. Okay. Also, we need to maintain the sum on this run. It should be the sum that if you fill all empty cells, what expected sum digits should have. And also for run, we can maintain mask. It is mask of allowed digits. You see that all digits in run should be distinct, should be different. So if you put one digit, it is not allowed to put it again in this run. So initially this mask can be complete for each run, but during the calculations of brute force, we put some digits, and if we put digits D, for example, here, we should remove from mask bit number D. And actually, these triple of variables do not give you full information about can you use such digit or you cannot. For example, if you have complete mask and length equals to 3 and sum, say it is 6, it is not allowed to use digit 4 here, because if you use digit 4, only 2 empty cells remain, and the total sum for them will be also 2, but you cannot use 2 instances of digit 1 to fill them. So it is impossible to use digit 4 here, but you cannot see it from, for example, these 3 variables. And the array D helps us to find, to use this property. So you see, it is array, 3-dimensional array. The first dimension is the total sum on empty cells of run. The second dimension is the number of empty cells on run. And the third dimension is the mask of allowed digits for run. And for such state, we pre-calculate all digits that can be actually used as a digits here. For example, for this state, digit 4 will not be in pre-calculated results. And all we need is just to check all submasks to check all subsets of given set. And to say that it is allowed to use this subset if it exists. So it is usual and simple dynamic programming to pre-calculate some information from about run to avoid not necessary calculations. And now the solution is just parse the input. You need to write some code to parse it because it's not just sequence of integers. And after it, in this code, we prepare objects run. Run object is just empty. It is just run, and it characterized by 3 variables. As I told you, it is remaining empty cells in it, expected sum on empty cells, and mask of allowed digits. For example, if we look into some empty cell and want to decide which digits can I use here, we can use 2 masks from horizontal ren and from vertical ren, and just do bitwise AND operation for them to get narrow mask. And for each cell in RAN, we assign the RAN as object, so all cells in RAN share the same RAN. And let's do just brute force. And brute force maintains the number of empty cells. If it equals to 0, we finished. We can print the answer and queue it from the program. But if it is not finished, we need to choose next cell from which our brute force will continue. And it is a very important step here to choose it something like greedy. For example, if you have large field and some cells have multiple candidates as digits, but you have another cell for which digit is uniquely defined, it is always better to start from this cell. And if we speak generally, it is always better to analyze all the cells and continue brute force, try all possible digits for such cell for which number of ways to choose digit is minimal. It is some kind of greedy approach here, and actually it reduces the running time of algorithm in 3-4 times significantly. Okay, so here there is 2 nested loops to check all cells, and if it is empty, we can calculate the number of digits for them, and if number of digits in candidate cell is better, let's choose best result, and after it, let's try all digits valid for current cell. Put digit in all RANs, at most 2 RANs, exactly 2 RANs, for which the current cell is intersection, and go deeper here. And you see that for example, this method is for if I place digit D into RAN, I should exclude it from mask, reduce the expected sum, and reduce the length of run. And this code for specific run returns mask of allowed digits for this run, and you see that we do not return just mask, but we return dynamic programming, result of previously calculated dynamic programming to reduce number of bits here. Okay. I think it is all about this problem. Jury wrote many solutions, but I think that this one is the shortest and uses smallest number of optimizations to fit in time constraints. Okay. The next problem is C. It was problem B. Problem C has graph nature. And if we speak in terms of graph theory, it is about an empty graph initially, and we add edges one after another. And if there is a cycle after a step, each edge has two parameters, reliability and cost, and in a cycle, the less reliable edge disappears, and if there are many of them, the earliest edge disappears among them. And your goal was to find such order for given edges that the resultant graph, the total cost of all edges is, I believe, large, as large as possible, as big as possible. Okay. Let's look in it in details. It is easy to see that the result will not contain any loops, any cycles. And it is easy to see that if on some step, if you have a cycle, the most heavy edge will be deleted from it. And if you have several, weight is just reliability of an edge. If you have several equal edges which has equal smallest reliability, earliest will be deleted here. So, for example, it means that if two edges have the same reliability, it is always better to add later such edge that I believe cost is greater, all right? Because the edge with less cost will be deleted by this edge will remain. Okay, so if we look into if we fix the order for equally reliable edges, the resulting graph will be unique. It doesn't depend on relative order, how you add edges with different reliabilities. Because each time you will remove specific edge, and if we want to find an edge, if we want to find the resulting graph after it, we should do the following. We should take all the edges and sort them in such a way that edges with high reliability will be at first. And also, if two edges have exactly the same reliability, we should sort them using the second parameter, their cost, and put at the beginning edges having greater cost. So just for this solution, we can just sort edges by pair reliability and cost from larger values to smaller values in descending order. And after it, we can greedily add them to graph, maintaining the system without any cycles. It is just some kind of cross-call algorithm. Just use, for example, disjoint set union data structure and add all of them in this order. Do add them to DSU, no cycles. And all added edges, it will be exactly our resulting graph. And to find an order to print it, we should just at first print all edges which I believe shouldn't be added, right? Or exactly this set. Here in this solution, at first we print all edges which are not in the resulting graph, and after it we add all edges which are in the resulting graph. So it makes the answer for this problem. So the solution is just comparing function for edges, DSU data structure, read the graph, read an array of edges, sort edges, add them, very similar to cross-call algorithm, and construct the required order to print the answer. Okay. Problem D. Problem D was about some weird sequence. It has some nature, some random nature, and actually it is just function for us. We should not analyze some special properties of this function. We can just calculate next value using the previous value. And this sequence contains finite number of different values. That's why it always has a cycle, and in general case it has some path before cycle, and after it has some cycle. If we iterate calculation of this function. And the problem was to find the second appearance of a value and to find the first of such second appearances. Okay. It was ask to find it only and only if its index is not greater than 2 multiplied by 10 in 7th power. But it is easy to see that solutions based on some kind of memorization of all different values will not fit in memory, and it is difficult to use such approach. So we will use an approach which doesn't use much additional memory, just constant number of additional memory. Let's put 2 pointers, say A and B, to the first element, and let's move them together. But let's move the first pointer A on one step each time. A equals F of A on each step. And let's move pointer B on 2 steps each time. So you can think about it as pointer A has speed 1 and pointer B has speed 2. And let's see what happens. And it will be some time, then they will meet in some point. And it is easy to see that this moment will not exceed the sum of lengths of before cycle and the length of cycle. So this first time they will meet, it will be for sure if it is U, and U is the length of path before the cycle, and V is the length of cycle. And it is easy to see that they will meet at the first time in some moment of time which doesn't exceed this value. If we will not find the meeting in this number of steps, it means that we should print -1 and queue it from the program. Okay, we have found some point on a cycle, but we do not know anything else. Let's find the length of cycle. You can just move 1 point forward and forward, forward and forward, until it meets this state again. So now we know not only some point on cycle, but also we know the length of cycle. This value is known for us for now, but our goal is to find this point, this value. Actually, it is not hard to find it. Just use 2 pointers again. A and B. And before the movement, you can send pointer B forward on the number of steps equals to the length of cycle. Just move point B zero. Such number of times. Okay. Now, before the beginning, it could be somewhere. It is not necessary on cycle, because maybe the path before the cycle could be longer than the cycle itself. But now let's move them together. And it is easy to see that on each step, the distance between them will be the same, and it will be exactly the length of cycle. We will move, at this step, we will move them both with speed 1. And it means that they have difference in indices equals to length of cycle. And it means that first time pointer B, pointer A reaches this position, pointer B makes full cycle and also reaches the same position. So first time they will meet, it will be exactly the position of our answer. So the solution is, it is slightly different maybe, but let's move both pointers and they meet on some point on the cycle. We can find the length of the cycle. And let's start again from scratch. Move pointer B forward to the number of steps equals to the length of cycle. And after it, you can move both of them with speed 1. And we should stop at the moment they will meet each other. So after it, we know the length of path before the cycle itself, the length of cycle itself. So the answer is just sum of these two values, just print it if it fits in the constraints. Okay. Any more questions? I think that an idea of two pointers is some well-known algorithm to find cycles, and this problem uses it and some extension around it. Okay, the next problem is meeting, and it takes me about an hour yesterday to find the solution for this problem, because during the contest 8 years ago I didn't solve it by myself, and but yesterday I found easy and short solution. I think it's nice. The whole solution is here. Okay, the problem was about a segment of length L and 2 points. One point is moving initially moves from the left end to the right end with speed v1, and another point moves from the right end to the left end with speed v2, and if a point reaches end point, it turns back and continues to move in the opposite direction. Okay, and also it was given the value t And it means that the problem was to find the number of their meetings during first t seconds of the process of their movement. Okay. We want to count the number of their meetings. And there are two different types of meetings. They can meet each other face to face when they have opposite directions and meet. And another case is they can meet each other if one of them has greater speed and moment, then it becomes forward comparing to the first point. So it is the second type of meetings. Then they have velocities in equal direction. Let's count each of them. If we speak about first type of meetings, it is easy to see that they both cover that we should sum their speeds. And for example, first time they will meet, they will both cover complete length of the segment L. The next time they will meet, they both cover distance of 3 lengths of L, because it means that they are at the same point, and so on. So we should add their speeds and find such number. Let's find the sum of their speeds, and let's find such number of moments t that the resulting past distance is exactly some odd number multiplied by L. But t should not exceed t uppercase. So we can easily find, let's do let's find all possible values m1 or ma here, ma. Let's find all possible integer values ma for which such value t exists that it does not exceed t uppercase. It is just this highlighted expression. We should substitute t uppercase here and do some transformations. But actually, we need not all possible values of ma. We are interested only in odd values. So we need to find odd values less or equal than ma. And you can easily find it by code like ma plus 1 divided by 2. It is number of odd numbers not exceeding value ma. So the number of meetings of the first type equals to the highlighted expression. And it is very similar that if we are finding the number of meeting of the second type, we should just subtract one speed from another speed and use it as their relative speed. So I have two variables, a and b, a for sum of speeds and b for the difference of speeds. And exactly the same expression I have to calculate the number of meetings of the second type. And it could be great if we could just print Ka plus Kb as answer, but it's not as easy. Because sometimes we have two meetings of different types at the same time. And that's why some meetings are calculated twice here. And all we need to find the number of meetings which were calculated twice and subtract them from the result, and after it just print the result. So the highlighted code needed to find the number of meetings, the number of moments of time that do not exceed t uppercase, and in that moment both types of meetings happened. Okay. Let's write some equations. What does it mean that meetings of two types happened at the same time? It means that you cannot for sure decide what is the direction of each of some point, and direction actually is undefined only on the ends. So it is just number of meetings at the ends of the segment. So, but we can just write, just now we can do not think about it, but just write an equations to find some properties. VA multiplied by time t should be equal to some odd number, integer odd number, multiplied by L. It means that at the moment time t, meeting of the first type happened. And the same, VB multiplied by t equals to another odd integer multiplied by L. Okay. We can just divide one equation into another equation, and the result will be VA divided by VB equals to 1 odd number divided by another odd number. And you see that if VA and VB has some common divider, it will disappear in this fraction. So an existence of such cases exactly the same as we can divide VA and VB, both of them, on their greatest common divider. And the results should be odd for first, for the value VA and for the value VB. And if it is not truth, so it will be no such time moments, then we have both types of meetings at the same time. So here I calculated GCD of A and B. I divided both of them and checked that both values are odd. Okay. But now we have another question. We need to find the number of time moments of such events. Look into this expression, and here we can substitute VA divided by VB on our variables AD divided by BD, because their common divider disappeared. So AD divided by BD should be equal to some odd number divided by another odd number. Or the same is AD multiplied by AB should be equal BD multiplied by OA. And you see that AD and BD are relatively prime. They do not share any divisors. So OB should contain all the divisors of BD. So OB is just BD multiplied by some odd integer. And OA should contain all divisors of AD. So it equals to AD multiplied by some by some odd integer. And it means so that OB is BD multiplied by some CB, and CB is also odd because OB should be odd. And exactly the same OA is AD multiplied by C. And it is easy to see that the value C is the same for OB and OA. It is the same value because we need to have this equation. And so this code is needed to find upper value for variable C from the first equation, to find the upper value for the variable C from the second equation, and as C is the same for the first and second equation, we should choose minimal value between them because we have two upper values. And how can we find this equation? Look at the first equation, and now we understand that OA is just A, D multiplied by C. So equation now is the following. And we know that T should not exceed T uppercase. So this inequation should be truth. And now we know all variables except C, and it gives us upper bound for C from this expression. And you see the following, the highlighted line is exactly the line to calculate upper bound for variable C. But we need not actually C. We need only odd values of variable C. So we used exactly the same trick as before to find number of odd values not exceeding specific value. And we do it for the first equation, for the second equation, and we need common time of moments. So just take minimum between RA and RB and subtract it from the result. So you see, it is this problem has very short solution, but it's not easy to come up with it, at least for me. Okay, problem F, the monochrome picture. The problem was to remove the minimal number of elements from the sequence in such a way that it will be no two neighboring positions that differs by exactly 1. So this condition should hold for the results in sequence, and we should remove the minimal number of positions, the minimal number of elements. Let's use dynamic programming here. The constraints were high enough. Let's use DI as minimal number of removals. Minimal number of removals on prefix ending at the position I. To satisfy the requirement, and position I cannot be removed. So I cannot be removed. So we leave the position I as is, as it was. Okay, actually, if we calculate the array D for the given array, it will not give us an answer for the problem easily. but we can add fake element to the right of our array, and with some unexpected value which for sure differs from all previous values for at most once. For example, I'm not sure about the values from 0. So for example, -2. -2 is good value because it differs from all previous values for at least 2. And if we calculate d of n here, because this position n minus 1 and our new fake element has index n, it will be exactly the answer on our problem. Because we leave this element, we can remove elements on the prefix, and we should satisfy, and it should satisfy the condition from the statement. Okay, let's calculate d from left to right, and if we calculate it in naive method, we will have quadratic time. What is the naive method? We want to leave position I as is. Let's find the previous position which should be untouched, say j. And all positions between them will be removed. So we can try all possible values of j and try to find minimum among values. We are interested in only such positions j that aj can be previous value for ai. So aj minus ai, their difference doesn't equal to 1, and we can get dynamic from here and add the number of positions between them and take just minimal value of this function. Okay, and it gives us quadratic time because we need linear time to find each value of d. But do we actually need to try all possible previous values? Actually not, because we are interested only in few of them, at most 3 or values. D is minimal number of positions to remove. So we want to minimize it. If you have another semantics for D as maximal number positions to leave, it should be max here. Okay, and here it is easy to see that you do not need to try all previous values dj here, but you can just maintain a few best positions with different values of a on them. For example, if you have 3 of them, at least one of them fits you. So this loop can make just constant time of iterations, and instead of quadratic time you actually have linear time here. Another solution was to use some kind of segment trees to speed up such idea, but it wasn't necessary. Problem E. And the next problem is G. It was easiest problem here, just some implementation. I wrote function ends, which checks if given string is a suffix of another string, and just implemented the rules which were written in problem statement. Nothing to say more about this problem. Problem H, annuity payment scheme. The easiest way to solve it was a binary search. Here we had a monotonic function. If current value of monthly payment enough for us to pay the whole debt or not enough. It is easy to see that if we increase our monthly payment, we will pay more money during this specific time period, and so on. So just use binary search for float operation, for floating numbers. For binary search, I prefer to use fixed number of operations, and I suggest you to use the same. It is not good to use, for example, here something like this. It's not good. Just because your function can have very big derivative here, can grow very fast in this point, and if you have a mistake, just epsilon here, you can have big mistake in value. Maybe this function is not such a kind, but in another problem you will find such function, and you will get some kind of wrong answer on test 100. So I always prefer to use fixed number of operations here. Also, it is very important for binary searches, for floating numbers, is to avoid usage of epsilon in comparisons here. Because if you use some epsilon to compare, for example, floating numbers, this epsilon shifts your result, shifts your answer to the left or to the right. You just shift your result, and it can give you a significant mistake in the results of binary search. So avoid to use epsilon in functions which are nested to binary search. Just here I do not use epsilon here to compare to floating point numbers, because for me it doesn't matter if it will be true or false if they are very, very close. Okay, and it is usual binary search. Just try the middle of the segment and simulate the process to pay each time exactly X money, And if some debt remains unpaid, so x is small for us, and we should move left bound to the x. Otherwise, we should move right bound to the x. I saw some solutions which do not use binary search here. They are short and maybe simpler, but for me it is just 2 minutes to write such kind of solution. Just look at the statement, see that, oh, it is monotonic function, and let's do binary search, and continue to solve the next problem. Problem I. I believe that problem I was the most interesting problem here. And it is very important problem to understand network flows better. The problem was about directed graph. Each edge has capacity. It may contain cycles, never mind, it doesn't matter. And there are capacities, positive capacities on a negative on edges, and you should make as many trips from source to destination, each time going through some path with positive capacities and reducing capacities by 1 on path. You should do as many trips as you can, and at the same time there were some edges, very important edges, which should be filled completely. We should, if we had initial capacities C1 and C2, for example, on them, you should have exactly C1 trips going through it, and exactly C2 trips going through second important edge. Also, if in one trip it was allowed to travel multiple times along edge, and in this case we should reduce capacity several times, as many as number of trips for this rod, this edge. Okay, so in terms of network flows, we need to find such maximal network flow to completely fill the specified set of edges. It is, and also we should represent it as paths, but it is an easy part of problem here, because each network flow can be separated on paths using greedy algorithm. Just go as flow goes, and extract one path, another path, and so on. So let's find the size of our answer, the maximal number of paths, or exactly the same, the maximal flow can be here to completely satisfy given set of edges. The solution will have two parts. One part, we will find any flow to satisfy requirement about important edges. And after it, we will improve extent found flow to be maximal, maintaining the property that it satisfies all important edges. And the second part is easier. For example, if for some for edge like not important edge, we have two constraints that flow by going through usual regular edge doesn't exceed the capacity, and it means that in terms of network flows we should add to our graph just two opposite edges, one of them with capacity C and the opposite with the capacity 0. It is exactly as usual. This part of code is very similar for me for different problems about network flows. It is just add typical regular edge from X to Y with capacity C. So forward edge has capacity C and backward edge has capacity 0, because it just means that if we look the flow on opposite from going through in opposite direction, it should be less or equal than 0, but we can it is easy to see that it means just f not less than 0. Just multiply on -1. Okay. And if we speak about important edges, we should find two constraints to make them exactly of specific flow. We want to be sure that flow going through an important edge is exactly C. And it means, in terms of inequations, that F is between C and C. And this part of inequation means just that forward edge should have capacity C. But this part of inequation, let's multiply it by -1, means that the opposite edge should have capacity -C. And it is just a requirement to be sure that the flow is exactly equals to C. So when we add important or historical, as it were written in the statements, edge, I used exactly the same code, but backward edge has capacity -C. In network algorithms, it is no any issue about negative capacities. It is absolutely good for them, except one small issue, that usual graph network flows algorithms start from zero flow as a valid flow, and they try to increase it. But here, if you have such constraints, zero flow is not valid. So we need some method to find any valid flow, and after it we can use typical network flow, any network flow algorithm to extend the flow and to find maximal flow which satisfies all the conditions about edges. So now our problem is to find any flow which meets all the conditions for capacities, including negative ones. And this problem is a little bit standard problem on network flows. Consider simple case if we have exactly one historical or important edge. It is important. It has capacity C capital, capital C, and all other edges are not important. S and T. So we need to find right now any flow which completely fills this edge. Consider we have such flow. It goes from S, flows, 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 and finishes in T. Let's make it not flow but circulation and add edge from T to S and return the excess here from T to S. So now it is just circulation, but it is also meets the requirement about important edge. And after it is closed system of, for example, water. We cut the edge. What happens? Now the edge is broken and some water starts to pour from this end, and this end wants to get some water. And as this edge was completely filled, the flow going out from this end equals C capital. And the flow which wants to be, which incomes to this end should be equals C capital. And we can add one extra T capital and S capital, two extra vertices, this and this. And if we find here right now, let's forget about current flow, and let's find again maximal flow from S to T. And if this maximal flow has size, has value C capital, it means that this edge and this edge are completely filled, and you can glue the edge again, you can repair it, you can break this edge, and as a result you will have some valid flow. It will not be maximal, but you will have some valid flow which satisfies the constraint for the given edge. But if you have 2 or more such important edges, it just means that you should cut each of them, and the incoming degree of t uppercase, is exactly the number of important edges. And the outcoming degree of uppercase S is exactly also the number of such important edges. So the idea is to add extra edge from old destination to old source, and the capacity of it is just infinity, because we do not want to restrict network flow here. After it, we cut each important edge and rebuild the graph, adding new source, new destination, and connecting them as it is on the blackboard, and find maximal flow here. And if all these edges, it is exactly the same as these edges, are completely filled by the found flow, we can transform graph backward to the original, and it will give us some network flow, not necessarily maximal or minimal, some network flow. The size of flow equals to the flow coming from T to S by our extra edge. So it makes us a method to find any flow satisfying the requirements. And after it, taking this flow as initial, we can use any flow algorithm to enlarge the flow, maintaining the requirements about capacitors. So the solution is just edge our graph, add regular edge, add historical edge, network flow algorithm, just Edmonds Karp. We need rescan to find the certificate to our problem. We do not need these functions for now. And here, read an edge, store some information in map about an edge. If edge is usual, just add it. If it is unusual, you should not add it to the graph, because on the first part of your solution, you do not need such edges, important edges. Add 2 new vertices to our graph, S and T. Add extra edges from S to the ends of important edges, from starts of important edges to T. Add an additional backward edge. Increase number of vertices by 2. And find network flow, and sum is an expected flow value. The function returns actual found flow value, So if they are equal, so sum is 0, it is interesting case. But if sum is not 0, it means that we do not have any, we cannot find any flow satisfying the requirements about important edges. And after it, we should remove extra edges. We should add historical edges to the graph. We should find the flow. And it is our result, but we should print it as number of paths. And we can greedily find paths using the flow. But if we use greedy algorithm to find paths, it is possible that we will find some paths from S to T. But it will be some cycles, some network of value 0, so some cycles that will not be part of our cycles. And we can just find such cycles and add them to the found paths. So here you see that we have found maximal flow. The size is max f. So the same number of times we just go from A to B here. It is just easy greedy way to find a path using network flow from A to B. And after it, just check all edges. And if there is a flow through edge, you can find any cycle containing this edge and append and add this cycle to some path, previously find path, and return the result. I believe that this problem is very important to better understand network flows, especially to understand negative capacities. So if you need to find maximal network flow on graph with negative capacities, you cannot start from 0 flow. And you need to do some additional steps to find initial flow, and after it to find maximal flow. The next problem is choreographer problem, problem J. Whether given two values n and k, integer values, and your goal was to find a sequence of all possible subsets of n elements, and the size of each subset does not exceed k, that for two neighboring subsets, we can think about them as bit masks. One mask and next mask, and for two neighboring masks, they differ either in exactly 1 bit in such case, or in opposite. We can replace 0 by 1 or 1 by 0, or we can move a bit from to the left or to the right. Such kind of picture or another. And your task was to find such order of bit masks that every two neighboring masks meet this requirement. The problem is very easy. Just here is a solution. Let's do some recursion here. And using recursion, let's build our answer as for n minus 1 and k. So you can think about it as at first we build our answer with series of values for which the rightmost bit is 0. If the rightmost bit is 0, we can think about that it is absent, and we build at first build the answer for n minus 1 and k. And by construction, our sequence will always start with a lot of zeros, and it always ends with the state 1 and many zeros. So the first line here will be many zeros, and the last line here in the first part of our solution, it will be 0, 1, and many zeros. The first column is 0 because we reduced the value n by 1. And now we should append to this part another part, and let's do it. Let's find the same sequence, but we can reverse it. And additionally add 1 bit to the rightmost column. So here we write many ones. And as you remember, this function returns rows from complete zeros to this one. So now the first row of the second part will be as follows. And you can easily see that between first and the second part, we meet the requirement. And the end will be many zeros from this function, but do not forget about the first one was added, and it seems that we constructed our sequence for n and k. And here the solution. And the last problem, k, wiki lists. It was a problem about converting wiki markup language, some small subset of it into HTML. And here it was not so hard to write also recursive solution. You could just write a function which processes a series of lines on a specific level. So you can just iterate through lines if all of them have the same prefix of the given length, they all belong to the same level or some nested. So unfortunately I didn't copy the solution to it, but you can make just a small recursive function to check if you have two neighboring lines which starts from after the prefix which starts from sharp character or from star character. It means that you have nested list and just process it and so on. Okay, I think we have short time for our lecture. So we have 5 minutes delay and we will continue with some new topics. Thank you. I think that right now we have short time to cover all topics which I planned for you, but that's why maybe our lecture will be a little bit longer, for 15 minutes, but let's start. And as a last lecture, I decided to switch from string algorithms to graph algorithms, and I decided to give you some introduction to bipartite matching problems. Or actually many facts will be about just general matchings, not bipartite. Okay, today we will speak about undirected graphs, and if we speak about some kind of matching problems, there are 4 problems where touching this field of knowledge. The first of them is matching, maximum matching problem. You are given undirected graph, and matching is such subset of edges that no 2 edges from the subset share a vertex. You may think about it as an independent subset of edges. It's easy to see that an empty set of edges is matching, but we are interested in maximal by size subset. So here we can find 3 independent edges here. For example, this edge, oh, I can use another color. One, 2, and 3. It is impossible to find 4 edges which are a matching. Okay. In practice, there is an easy algorithm to find maximum matching in bipartite graph. Bipartite graph is a graph which vertices can be split on 2 disjoint subsets, say A and B, and each edge comes from A, from some vertex of A to some vertex of B. Usually we can draw them like this. It is A, it is B, but it doesn't mean that bipartite graph is always giving you like one part of vertices and another part of vertices. For example, this graph is also bipartite because such division into 2 sets A and B exists here. For example, A, B, A, B, A, B, A. If all vertices are labeled with letter A, we put them to the set A, and all vertices labeled with letter B, we can put them to the set B. it is easy to see that each edge connects vertices from different sets. Okay, but for example, this graph is not bipartite, and there is easy and short algorithm to find maximum matching for bipartite graphs, but algorithm to find maximum matching for general graph is very complicated, and for example, my teams on World Finals only had it in team reference materials, but they were not able to write it from head without team reference material. Okay, it is matching problem, and we have Koenig's criterion that graph is a bipartite. Graph is bipartite if and only if all cycles of a graph are even. If we have at least one odd cycle, graph cannot be bipartite, because if you have odd cycle, let's label its vertices in two colors A and B, and you will see that it will be a moment, it will be always a moment then you need to put two equal labels as endpoints of single edge. So graph is bipartite if and only if all its cycles have even lengths. Okay. Another problem. This problem is MM, maximum matching problem. Another problem is minimal edge cover. And in this problem, you need to cover all vertices using edges. So edge covering is such set of edges that any vertex has at least one edge from the subset, and it is endpoint of this edge. So at least one edge from the subset touches each vertex. It is easy to notice that if we have vertices of degree 0, isolated vertices, no cover exists. But here we can easily find it, and for sure if there are no isolated vertices, we always can take all edges. But we are interested to minimize the number of chosen edges. So the problem is to find such minimal subset of edges to cover all vertices. And here I can show you an example of, no, I'm wrong about it. Here is example of minimal edge cover, minimum edge cover. And we have more two problems. They are the similar, but they are about vertices. Let's use the same graph. And minimum independent vertex set is a such subset of vertices. Maximal independent vertex set is a such maximal by number of vertices is such subset of vertices that no edge connects two vertices from the set. So it is independent. And for sure, empty subset is independent, but we are looking for maximal by size subset. And here, for example, we can use this subset as maximal independent vertex set. And the last problem, you can help me to find the statement for it, because about edges we have two problems for independent set of edges, and we cover vertices by edges. Here we already have a problem about independent set of vertices. So here we want to cover all edges by vertices. Minimum vertex cover. We have the same graph, and vertex cover is such subset of vertices that each edge has a vertex from subset, at least one vertex from subset as endpoint. So each edge is covered by a subset of vertices. Here we can use just free vertices. And it is easy to see that each edge has blue vertex as at least one of endpoints. Okay, and we have 4 problems here. All of them are connected with each other, and I'll show you how they are connected. The most easy part here is to find connection between problem 3 and problem 4. Let's look into any independent vertex set. If you have independent vertex set, and you have remaining vertices, so all edges go inside this subset or from this subset to independent vertex set. It means that if you take complement to this subset, if you take this, it will be vertex cover. It is easy to see that each edge has a vertex from this subset as endpoint. And it is exactly the same to the reverse direction, to the opposite direction. If you have any vertex cover, it means that edges either inside this subset or go from this subset to other vertices. And it means that if you take complement of vertices from vertex cover, they will give you independent vertex set. So maximal independent vertex set and minimal vertex cover are connected just with simple equation. Just they are complementary for each other. So you can find one of them and take complement and you will get another of them. As a result, it is easy to see that if you find the total size of maximal independent vertex set and the total size of minimal vertex cover, you always will have number of vertices in graph. Okay, it was easy. What about edges? It is very likely to say something like, oh, it is maybe similar, and maybe the number of edges in maximum matching plus number of edges in minimal edge covering, say it is M. It is completely incorrect, and it is surprising that their sum is also N. If you take, you see here, we have 3 edges in maximum matching, we have 4 edges in minimal edge cover. Size of maximum matching plus size of minimal edge cover is also N. And let's show it. And let's show how to build one of them using another and vice versa. For example, consider we have some maximum matching. So it is a set of independent edges. If a vertex belongs to maximum matching, we will say that it is matched. So we have 2 multiplied by mm number of matched vertices. But we also have all the remaining vertices, and they are unmatched. And we want to color them. We want to build we want to build edge cover using maximum matching. So we already covered 2 multiplied by mm vertices, but we didn't cover yet n minus 2 multiplied by mm vertices. Let's look into all edges going out of such vertices. Can we have an edge like this, which connects 2 unmatched vertices? No, because if we have such kind of edge, we can add it to our matching, and it will increase our matching, but it is maximum. So no such kind of edges. So if you look into unmatched vertices, their edges go only to matched vertices. And what is the minimal number edges we need to use to make edge covering from maximum matching? We should just take any edge from any unmatched vertex and use it. So if we have maximum matching of such size, we use edges of maximum matching, and also we use additional edges to cover all unmatched vertices. And the number is, I wrote it. So using maximum matching and some kind of greedy algorithm, we have constructed edge covering consisting of such number of edges. And it means, maybe for now we are not sure about is it minimal or not. Maybe we have another algorithm, maybe we should start not from the maximum matching, but right now it is fact that so the size of minimal edge cover is not greater than n minus size of maximum matching. Actually, you can be sure that it is equal sign here. And here there was a way to construct edge cover by maximum matching. And let's do in opposite direction. So we have some edge cover, and it is minimal edge cover. Minimum edge cover. Can minimum edge cover contain a cycle? Is it possible to have such kind of minimum edge cover? No, sure, because we always can remove it, and it will not change the set of covered vertices by we reduce the number of edges. So for sure minimum edge cover is a set of trees. Also we do not need this fact, but it is easy to prove that the diameter of any such tree cannot be greater than 2. Because if we have, for example, tree with diameter 3, we can always remove this edge. It will reduce the number of edges, but the set of covered vertices will be unchanged, remains. Okay, so our minimal edge cover looks like this. It is a set of disjoint trees, and if you have set of disjoint trees, the number of edges in it, number of edges is just MEC, size of MEC. It is n minus number of components, number of trees. If you have 1 tree, it contains n minus 1 edges. If you have two trees, they both contain n minus 2 edges, and so on. But let's build some matching, taking exactly one edge from each tree. For example, we can take this edge from this tree, this edge from second tree, and this edge from the third tree. And it is easy to see that it is matching, because trees are disjoint. So now it is matching, and it contains k items, k edges. So we found some matching having exactly such number of edges. So, but possibly it is not optimal algorithm, and maybe we can find something better. And it means that the size of maximum matching is at least n minus size of minimal edge cover. And comparing this inequation and this inequation, it's easy to see that they are both are equations. So as a result, size of maximum matching plus size of minimal independent minimal edge cover equals to n, and you have easy way to construct them of them from another. So right now, if we look into our 4 problems, we found connection between third and fourth problem and between the first and the second problems. But right now, no connection between them. And this connection exists, and it has a name, and a name is Koenig's theorem. Koenig's theorem. Initially, Koenig has formulated the theorem not about graphs but about binary matrices. If you have binary matrix containing only zeros and ones, the theorem is following. The maximal number of independent ones, I'll tell later what independent means. The maximal number of independent ones equals maximal number of independent ones equals to minimal number of lines to minimal number of lines to cover all ones. And independent ones mean that they are not share the same row and the same column. You can think about it as you can place chess figure rooks on ones, and no rook will attack another rook. They are all be in the different rows and columns. It means independent. And number of lines here mean a row or a column. It's up to you to choose columns, rows, but For example, here we have two lines to cover all ones. One line and the second line. And also here we have at maximum two independent ones. For example, one from here and one from here. They are independent. But we cannot find three independent ones. It is easy to see that this theorem actually is about graphs. Let's build bipartite graph, and vertices A, it will be rows, A, rows, and vertices B, it will be columns. And if we have one on intersection of a row and a column, it means that they are connected in our graph. And I can use, we have 3 and 1, 2, 3, 4, 6. And 6 vertices on the right, and we have something like this, and something like this. And if we speak in terms of graph theory, there is a bijection between such binary matrices and bipartite graphs, and the set of independent ones is just a set of independent edges here, and vice versa. The set of lines to cover all ones is a set of vertices to cover all edges here. So Koenig says that for bipartite graphs, size of maximum matching equals to size of minimal edge cover. And later I'll show you the way to find, say, minimal edge cover using maximum matching. And that's why problem 1, problem 2, problem 3, and problem 4. I'm sorry?
The size of the maximum matching equals the size of the minimum vertex cover?
Minimum vertex cover, sure. My fault. Minimum vertex cover. And returning to our problems, we have connections like 1 and 2nd, 3rd and 4th. And these connections are not for bipartite graphs, but in general. But for bipartite graphs, we have a connection between, say, these. It is not important. We can always take complement of set of minimal vertex cover to get maximal independent vertex set. But we have such kind of connection, and in practice it is, if you need, for example, minimal vertex cover or maximal independent vertex set, it is always easier to find maximum matching and transform it to MVC or MIVC, VS. It is bipartite. Let's continue. And now I'll show you an easy way to construct maximum matching Consider we have bipartite graph. We have bipartite graph and some edges belong to some matching. Okay, we have bipartite graph and matching here. And a path is alternating if moving through path, each two neighboring edges has different type how they belong to matching. Belong and do not belong, belong and doesn't belong. So, for example, alternating paths here are 1, B, 2. You see it is alternating path because matching alternates in path. Also, for example, just go from C to 2. It is also alternating path. Why not? It is very short alternating path. And let's find some longer alternating path. For example, 1, B, 2, D, 4. 1, B, 2, D, and 4. It is also alternating path. But actually, we mostly interested in augmenting paths. If a path, if alternating path starts from unmatched vertices, unmatched vertex, and ends in unmatched vertex, it is augmenting. Starts with unmatched vertex and ends with unmatched. Here, an example of such path is 1B, 2C. 1B, 2C. Such path always starts from an edge, not from matching, and also such augmenting path ends with an edge not from matching. So it has a form unmatching, matching, unmatching, matching, unmatching, matching, and ends with unmatching. And that's why augmenting path always has odd lengths. Odd lengths. It means that it starts on one part and it ends in another part. If you have augmenting path, you can easily increment number of edges in maximum in matching, not maximum. If you have matching and you found some augmenting path, you can reverse the path. You can extract from matching all edges from matching which belong to the augmenting path and add to the matching all edges from augmenting path which were not in matching. So we do the modification here. If we have augmenting path, we can remove this edge from matching, but add two edges to matching. And such transformation for sure will increase the number of edges in matching by 1. And from other hand, for sure, the set of edges continues to be matching. We can use symmetric difference symbol. It is something similar to exclusive OR in programming. Current matching, augmenting path. We can find symmetric difference of them, and it will be our new matching. So we now are sure about the fact if there is an augmenting path for current matching, this matching is not maximal. And the opposite fact is also the truth. And it's called Birch theorem. And it is very important that this theorem is not only for bipartite graphs, but it is for graphs in general case. Matching is maximum. Matching is maximal. Matching is maximal if and only if no augmenting path exists. It is easy to see that, and we already did it in one direction, but what about the other direction? It is also easy to prove. Consider we have matching and no augmenting path exists. We have matching. and no augmenting path exists. But let's prove it by contradictory. Imagine that there is another, that this matching is not maximal, and there is another matching, greater, larger matching. So we have matching M, our matching, and matching M strike, and our matching is less. Let's find their symmetric difference. I mean that we can look into such edges which belong to exactly one of matchings. If you look at them, it is easy to see that vertex can have only two edges to touch it. One edge from first matching and one edge from another matching. Okay, let's find set of edges F is symmetric difference for M and M sharp, M strike. And each vertex has degree 0, 1, or 2 if you consider only edges from F. And it means that the graph seems like paths and cycles. But we cannot have path of odd lengths there. Because if we have path having odd lengths, it means that it starts from edge of M strike. After it, there is an edge of M. After it, edge of M strike. After it, edge of M. And it ends with edge of M strike. And it means that we have augmenting path in M. But we do not have augmenting path. So all paths are even by length. And also the same is for cycles, because we can consider any cycle, and in this cycle edges are any two neighboring edges differs one edge from M and neighboring edge from M sharp, M strike. So all cycles are also even. And it means that in this set, the number of edges from M equals to the number of edges from M strike. And also we can consider edges that belong to the both sets. They are also equal number of them. So it means that size of M strike equals to size of M, and Birch theorem is correct. Okay, so, and we did not use that graph is bipartite. It is correct in general case. So it means that simplest way to find maximum matching is just the following. Initialize current matching by empty set it is matching. Empty set is always a matching. And while exists P, that P is augmenting path, modify M by this path. It is idea for simple algorithm to find maximum matching, and this idea doesn't use that graph is bipartite. The issue is it is very easy to find augmenting path for bipartite graph, and it is harder, it is more tricky to find augmenting path in general graph. And if we have bipartite graph, and we want to find augmenting path, we should give a direction for each edge. Let's give direction from right to left for edges of matching, current matching. And let's give direction from left to right to all other edges. And after it, we can take all unmatched vertices from part A and use DFS, BFS, any of them to find paths to unmatched vertex from part B. If there is a path from unmatched vertex from A to unmatched vertex from B after we constructed the directed graph, it means that augmenting path exists, and such path is just path from unmatched vertex here to unmatched vertex here. But if there is no such path, it means that no augmenting path exists. But there is a very nice implementation of this idea called Kuhn algorithm. It do exactly the same, but has nice implementation and very short and easy to write. We can maintain our matching using array MT, and this array is indexed by vertices of the second part. And if vertex B is unmatched, the array contains -1. B is unmatched. If vertex B is matched and its pair vertex A, we use A as value in MT. A, B, edge AB belongs to M. And on each step, on each iteration, Kuhn algorithm tries to find augmenting path from vertex of A. So we can initialize MT with -1s. The length of MT is size of the second part of vertices. It is size of B. And let's go from through vertices of the first part. And now here we will try to find augmenting path from vertex A, and to do it we will use depth first search, and to do depth first search we need used array of visited vertices. So and the size of array used is number of vertices in A, because we maintain it for the first part of vertices. And now here we are trying to find one more augmenting path, and the following code will not only find the path if it exists, but also it applies the path and it will change our current matching. So if let's try Kuhn function. MM is the size of our matching. This function tries to find augmenting path from vertex A and returns true if it found the path. So if we found the path, we increase the number of our maximum matching. It is exactly the same as to count the number of non-negative values in MT after the calculation here. It is exactly the same, but we can just use counter to count them. And function Kuhn it makes depth first search. So if it visits previously visited vertex, it should return false because it is invalid state. After it marks vertex X to be visited. And it iterates through all neighbors of X, say Y, it means y is neighbor of x here. It is just usual depth first search. And if vertex y is not matched, for sure we have found augmenting path, because we found our path returned finished in some vertex which is unmatched. Or if vertex is matched, we should return by this edge, because there is only one edge which belongs to matching and ends with y. We have only way to continue our search is to return by this edge. And if we return by this edge, we just call kun of mt of y. And we return and continue our search. If search finished with success, the function returned true. It means that we found augmenting path, and we can match our neighbor y with x. So here we should do something like mt and immediately return true. And after the cycle, return false if we did not found augmenting path. And that's the complete code to try to find augmenting path from vertex x. But there is one tricky question here. You remember the only way to find augmenting path is to start from unmatched vertex. But looking on Kuhn algorithm, they did not check it. Why vertex x, vertex A, is unmatched here? And the answer is yes, it is for sure unmatched because of property of Kuhn algorithm. And the property is the following. It is a very important property. The property is after kth iteration of the main cycle of Kuhn algorithm, it maintains the maximum matching for subgraph if we remove all these vertices. But these vertices will be in our graph. It maintains maximum matching for such subgraph. And it is a kind of dynamic programming. It adds one vertex after another to the first part until it becomes complete first part. And it is the first property. After the iteration k, Kuhn algorithm MT is maximum matching for this subgraph. And the second important property, it is easy to see that if some vertex was matched, it cannot be unmatched again. And it means that this algorithm tries very much to match the first vertex. And if maximum matching exists, such matching that covers the first vertex of the first part. If such maximum matching exists, this vertex will be matched after the first iteration of Kuhn algorithm. It is some kind of greedy algorithm. It makes everything it can to match the first vertex. After as the second option, he tries to match the second vertex here, and so on. So, for example, if you have weights on vertices of the first part, you have weights, and you want to find such maximum matching that total weight of all matched vertices of the first part is maximal. We do not have weights on the second part, just the first part. What should we do in this case? What is the solution here? We want to maximize the total weight of matched vertices of first part.
Sort the point by weight?
Yes, sure. We should sort points, sort vertices here by their weight from the greatest to the smallest, and use Kuhn algorithm in this way, in this order. And Kuhn algorithm will do always it can to match this vertex at first, second vertex, and so on. Okay. And I think the last topic here, but actually it is not all things I was planning to tell you. So we have easy way to find maximum matching. But there is right now no way to find minimal vertex cover or maximal independent vertex set using maximum matching. Let's find them. If you have bipartite graph and you already have maximum matching, let's do the same orientation for all edges as we did before. For edges of maximum matching, we orient them from right to left, and all other edges we will orient them from left to right. And let's use, for example, DFS to mark all vertices that are reachable from unmatched vertices of first part. We use DFS from all unmatched vertices of A. And say it is A and S is a subset of vertices visited by DFS on first side. And the same. It is part B, and T is vertices visited by DFS on the second side. In this case, you can find minimal vertex cover, for example, using A, using complement of S here, and vertices of T from the right side. And maximal independent vertex set is the complement of it. Just do the opposite operations. Let's look in details, for example, to it. It means that it is let's consider it as vertex cover. So we cannot have any edges from S to not T. If we have such edge, it means that it is incorrect. In opposite case, it means that it is correct. And you can easily show that it contains exactly expected number of vertices, because every edge of matching has exactly one vertex from this set as endpoint. And for example, if we have such edge, there are two options. It can be a part of maximum matching, or it can be not a part of maximum matching. If it was a part, it was oriented in this way. And it means that X, Y, vertex X is matched. So, but from the other hand, it was visited. So the only way, one way to visit it is to come back to it from X, from Y. But Y is unvisited here. So it is impossible case. We cannot visit vertex X from Y if Y is unvisited, by X is visited. So we cannot do it. But if this edge doesn't belong to matching, it means that on the first step, if this vertex is visited, it means that we should use this edge to visit this vertex. But this vertex is unvisited. So we have contradiction again. And it means that we can construct vertex cover using this equation. And I can stop for 5 minutes how to implement Kuhn algorithm much faster. Actually, it can be implemented in, actually right now it works in cubic time. But you can implement it, it is easy to see, that it will run in cubic time of n, where n is smallest part of vertices. For example, if you can two parts, one small and one large, you can implement it in such a way that it will run for cubic time of smallest part. Another idea, one more idea. Here, what option is more interesting for us what is faster? Use this option to return true or use this option to return true? The first one is just faster, right? So you can just use two cycles here. One first cycle should contain this condition without this part. And next cycle, if we cannot find augmenting path using unmatched vertex, we should go deeper. And the second copy of this cycle can contain, should contain these conditions, the second condition. It makes Kuhn algorithm faster. Another option, one more option. You can start not from empty matching, but you can initially build matching using some greedy algorithm and use it to start Kuhn algorithm. But in this case, you should be very careful about to check that you actually start this function from unmatched vertex, because it is not real Kuhn algorithm now, and if you will not maintain unmatched vertices of the first part, you will start this. You will start here from matched vertex because of greedy initialization, and it will return invalid matching. And the last thing I can show you, I prefer to use projector here. This trick will make algorithm very fast to run on thousands of vertices. Look, here we have Kuhn function. The only difference here that, yes, I used two separate cycles, as I mentioned before, to process neighbors. And also I used not only matching from second part to the first part, but also I maintain matching as array from first part to the second part. I needed to maintain unmatched vertices on of the first part. And the key idea here is the main part of algorithm. The main part here that actually we do not need to initialize used by false and start DFS from the scratch on each time. We can do it like this. We can just we can try to find augmenting path starting each time from unmatched vertex. And we do it again and again, again and again. If it was impossible to find augmenting path, it means that it is time to it's time to no. If we didn't find augmenting path, it means that we can leave our marks for that first search as is and try to find it. And we can do it in such a way. You can just take a photo of it and think about it after it. But this code tries not to make, not to clear the array used on each time, but it tries to keep it and continue to reuse it as long as possible. And if you have a bipartite graph and parts are about 500 or less, don't worry and use the simplest version. Do not think about such optimizations. You do not need them. But sometimes, and I saw it, you need to find maximum matching faster, and you can do something like this, and it can make algorithm significantly faster. Okay, I think that I finished. It's time to dinner, and thank you for your attention. I was glad to be here for these days. It was interesting for me, and I hope it was useful for you. Thank you.
Thank you for being with us. So I'd like to personally thank Mike for being with us again. And I have a few reminders for you. Lunch will be served in the same place we did last week. Please do not go to the wrong way. It's easy, just follow the guide. And we are going to have contests in a set of different rooms this afternoon. So you can only enter the rooms that have our boards. Brazilian ICPC Summer School. Other rooms are going to be used to other students. We have people over there to help you. I have just sent you a link to the certificates, so you should have received a PDF file with all certificates. Get your print or do what you want with your certificates. And I would also publicly thank to the student monitors that were helping all those 2 weeks. They come and go, and you almost never see most of them, but I would like to personally thank them on the video. So enjoy. This afternoon I'm going to